Suppose a friend has invited you to dinner and you tell them on the telephone that you think you can be there in half an hour. Then you go out to your car, and when you get to your car you see that it has a flat tire. Well, that might change the likelihood of your being able to get there in half an hour, mightn't it? You have additional information. So with additional information, you might need to change the probability that you can be there in half an hour. The topic of conditional probability has to do with changing probabilities based on new information that comes along. Suppose you're rolling a pair of dice. The probability the sum of the numbers on the dice is 9 is 4 divided by 36 because there are 36 possible outcomes, as we know, when you roll the pair of dice, and only 4 of those give you a sum of 9. You can have 6 on red, 3 on green, 5 on red, 4 on green, 4 on the red die, 5 on the green one, or 3 and 6. Those are the 4 ways you can get a sum of 9, and that's 4 of the 36 possible results. So probability 4 over 36, or 1/9. Now imagine this situation. Suppose you see that the red die shows the number 5, but you haven't seen what number is on the green die. Based on that additional information, what then are the chances that the sum on the 2 dice is 9? Once we know that the red die has the number 5 on it, we know that the outcome must be one of these shown, one of these 6 cases where the red die has the number 5. Of those 6 cases shown, only one of them shows a sum of 9, the case where the red die has a 5 and the green die has a 4. So the new information that we have in effect says that no longer do we have 4 chances out of 36, but we have 1 chance out of 6, because the given information, the new information that has come along, reduces us to these 6 possible outcomes, and only one of those 6 gives us a sum of 9. Here's the grade distribution on a class of students. For each grade, A through F, we show the number of students that have that as their current grade in the class. If a student's randomly picked from this class, what's the probability that we get an A student if we know that the student is one who's passing the class? How many students are in the class? Add up these numbers. 5 and 14 is 19, 26, 35, 43. So we have a total of 43 in the class. And if we just reached in the class and picked a student out of those 43, 5 of them are A students, so that would be 5 chances in 43 that the student that we picked is one of the A students. However, we're looking at the situation where we have additional information. We know that the student is passing the course. If you subtract the 8 who are failing from the 43, we have 35 who are passing the course. 5 of those are A students. So based on the information that the student is passing the course, the chances that it's an A student is 5 chances in 35 as opposed to 5 chances in 43, which is what it would be if we did not have that information. There's a very important definition for conditional probability, which is very useful in lots of situations if you're having a little bit of struggle with figuring out how to think about it. Here we have 2 events, A and B, A not being the empty set, so the probability of A is not 0. You can think of the conditional probability of B happening if we know that A happens as this fraction, the probability that both things happen divided by the probability that A occurs. So the way we read this, when we see this notation, P of B and then a vertical line and then A, we read this as the conditional probability of B given A. So what we're thinking of intuitively is what's the probability that B happens if we know the information represented by the event A, that is, if we know that A occurs. And the definition says that it's the probability of the intersection of the two events, which we can say verbally by saying the probability that both things happen, divided by the probability of A, that is, the probability that A happens. Let's illustrate with the example we've already considered, that is, the chances of getting a sum of 9 based on the knowledge that we had a 5 on the red die when we were rolling a pair of dice. Here we're letting A represent the event that the red die shows the number 5, and B the event that the sum of the numbers on the red and green die is 9. And we're thinking about the conditional probability of a sum of 9 based on the knowledge that the red die has a 5 on it. And the definition of conditional probability says we should be able to get that by looking at the probability that both things happen divided by the probability of A, which is the given information that there's a 5 on red. Thinking in terms of that definition, what would these two probabilities in this fraction be? B intersect A. The intersection of these two events says we're looking at the cases where there's a 5 on red and the sum is 9, and of course the only way that can happen is to have a 5 on red and a 4 on green. That's one of the 36 outcomes. So the probability of that intersection is just 1 over 36, whereas the sum is 9 can happen in the 6 ways that we saw earlier for a probability of 6 over 36. So the conditional probability reduces to 1/6, which is exactly what we saw when we thought through this problem earlier. So we're seeing this definition being consistent with what we had earlier arrived at thinking about the problem intuitively. Let's go back to the problem of selecting the student from the class. If we think of A as being the event that the selected student is passing the course, and B being the event that it's an A student that we've selected, then the question we're looking at when we look at the conditional probability is what is the probability of getting an A student if we know that we get a student who is passing the course. If we think about that in terms of this fraction, what is B intersect A? What group do you have if you take all the A students and intersect it with all the students who are passing the course? Well, of course, that gives you just the A students, doesn't it? Because obviously any A student is passing the course. So the intersection of these two sets is just A in this case, and the probability of A, that is that a student is passing the course, there are 5 students out of the 43 students in the class, so that was 5 out of 43 in the numerator. And the denominator, the probability of A, that the student is passing the course, well, we have 43 students in the class, 33 of them were passing, so that probability in the denominator is 35 over 43, and this fraction reduces to just 5 over 35, as we saw previously. See, the important thing that this definition does for you is it allows you to think about the conditional probability in terms of two unconditional probabilities. These probabilities in the fraction are the probabilities as they were in the original sample space before you arrived at any additional information. Now we have 5 people competing for 2 roles in a play. Let's assume that the 2 roles are to be randomly assigned. What's the conditional probability that Peggy gets a role if we know that Carol does not get a role? The first thing we want to do is to name our events. So let's let B be the event that Peggy does not get a roll, that Peggy does get a roll. That's the event whose probability we're wanting to calculate based on the information that Carol does not get a roll, which is what we're representing by the letter A. So the question, again, we have named our events so that the question that we're being asked is what's the probability of B happening if we know that A happens. Now, in order to get a firm understanding of what's going on, in this case, let's write out our entire sample space. Two people are going to get a role in the play, so let's write out all the possibilities for which two people get roles. We have 5 people, and 2 of them get roles, and we know from the combinations formula that combinations of 5 things choosing 2 is equal to 10. 5 times 4 divided by 2 is 10. And here what I've done is to write out the 10 possible pairs of people who get roles in the play. So take a moment to look at that and convince yourself that this is a correct list of possible outcomes. Now, in the context of this list, which of the outcomes make up the event A? A was the event that Carol does not get a role. So in looking at the list here, the outcomes that make up event A would be the outcomes where Carol does not get a role, that is the outcomes where Carol is not one of the 2 people listed. We have a line drawn through the 4 cases where Carol is one of the ones chosen, and that leaves 6 cases, case number 2, 3, 4, 8, 9, and 10. 2, 3, 4, 8, 9, and 10 are the cases where Carol does not get a role, so those are the outcomes that make up event A. Since we're randomly choosing the 2 people, these 10 cases are equally likely. 6 of those 10 cases belong to the event A, so since every outcome is equally likely, that means the probability of A is 6/10, 6 chances in 10. 6 of the 10 outcomes do not include Carol. The intersection of A and B says, look at all the cases where Carol does not get a role, but Peggy does. They are the ones that are shown in red. The red cases, case 3, 8, and 10, are the cases where Carol does not get a role, but Peggy does. That's the intersection of the 2 events. So the probability of the intersection is 3/10, 3 of the 10 cases. An alternate way to think about it is to think about, for P of A, Carol not getting a role, you can think of the total number of possible outcomes, all the ways of choosing 2 of the 5 people. But for Carol to not get a role, it means that the 2 people chosen have to come from the 4 people other than Carol. So what I'm showing right here, the combinations of 4 things choosing 2 and the combinations of 5 things choosing 2 is simply looking at it in terms of counting the possible outcomes in the denominator and counting the outcomes in the event A in the numerator using the combinations formula. And of course that confirms what we're seeing when we've actually listed the outcomes. And in the same way for B intersect A, the cases where Carol does not get a role but Peggy does, means when you're choosing the people to get a role, Peggy automatically gets one of them, so you have to have one of the other people in addition to Peggy, but not Carol. So that's where the C of 3-1 comes from. What I'm pointing out to you is simply that you can get these probabilities, 6/10 and 3/10, by doing the counting using the combinations formula without actually making a list like this. We first looked at the probabilities in terms of this list, but I'm reminding you that you know counting techniques which would produce these answers without writing down this list if you wanted to do so. So let's move on to think of the conditional probability in terms of the definition of conditional probability, which we just looked at. We should be able to get the conditional probability of B given A by thinking about the probability that both things occur divided by the probability of the new information that comes along. Both things occurring has probability 3/10, as we just observed. The probability of the new information, A, is 6/10. So when we fill in these two probabilities, we're looking at 3/10 over 6/10, which is 1/2. Now we've just answered this question using the definition of conditional probability, and I pointed out that you can do it without actually listing all the possible outcomes. But since we do have them listed, let's look at these outcomes and confirm that the answer we just got is correct by looking at it a simple intuitive way. The question is, what's the probability Peggy does get a roll if we know that Carol doesn't? Well, if we know that Carol doesn't, that eliminates cases 1, 5, 6, and 7. So we're left with these 6 cases that are not crossed out. From those 6 cases, the cases where Peggy gets a roll are the 3 red ones. So the question boils down to, what's the chances that the outcome that we observe is one of those 3 red cases out of the 6 cases that remain once we know that Carol does not get a roll? So that's 3 chances in 6, a probability of 3/6, which is exactly what the conditional probability formula just gave us. Now we have confirmed it by looking directly at the outcomes and seeing that that answer is correct. Sometimes it's useful to take the definition of conditional probability and multiply through both sides by probability of A and use it as a way of determining the probability of the intersection. Let's see an example where that's helpful. If we deal 2 cards from a standard 52 card deck, what's the probability that both are hearts? Well, treat that as a counting problem. We have to count the number of possibilities when we deal 2 cards from 52, and we have to count the number of possibilities where both cards would be from the 13 hearts. If we do those 2 combinations and then simplify the fractions, we get 1 over 17. So we can do this problem just as a counting problem. We don't need the concept of conditional probability in order to do the problem. What I'm going to show you is an easy way to do the problem, optionally using the concept of conditional probability. So I'm in effect going to show you a new way of doing this problem. But we already know what the answer is we're supposed to get because we can do this problem using methods that we already know. Let's think about it in terms of this version of the conditional probability formula. Think about dealing these cards one at a time. We're dealing 2 cards from a deck. Let's think about dealing them one at a time. And let's let A be the event described by saying the first card dealt is a heart, and B the event described by saying the second card dealt is a heart. In terms of these 2 events, B intersect A says what? B intersect A would be all the cases where the first card is a heart and the second card is a heart, which is simply cases where both cards are hearts, right? So probability of B intersect A is asking what's the probability that both cards are hearts. And remember, we know what the answer is because we just looked at the problem a different way. This equation tells us that we can determine that by multiplying these 2 numbers, the probability of A times the conditional probability of B given A. Now let's think intuitively about what those numbers are. Probability of A is just the probability the first card is a heart. Well, when you deal that first card, you're dealing from 52 cards in the deck, and 13 of them are hearts. So that probability, P of A, is going to be 13 chances out of 52. Now let's come to this conditional probability. This says, what's the probability of B happening if you know that A happens? In other words, what's the probability the second card is a heart if you know the first card is a heart? Well, if you know the first card is a heart, what's left in the deck when you get ready to deal the second card? After you've dealt the first card, which is a heart, you've got left 51 cards, of which 12 of them are hearts, right? Because you've already dealt one heart. So if you know the first card is a heart, then when you deal the second card, you're working with a deck of 51 cards, of which 12 of them are hearts. So that's going to be 12 chances in 51 that the second card is a heart, based on your knowledge that the first card was a heart. So when I multiply these two numbers, I'm multiplying 13 divided by 52 times 12 divided by 51. When I do that arithmetic and reduce the fraction, I come up with exactly the same answer that I already knew to be the correct answer. So we've given another solution to the problem using the concept of conditional probability, and it's a very attractive solution because the two numbers that I'm multiplying are intuitively quite obvious. Now let's modify the problem a little bit. We're still going to be dealing two cards from a deck, but the question now is, what's the probability that both are hearts if we know that at least one of them is a heart? So we'll redefine the events A and B. B now is the event that both cards dealt are hearts, and A is the event at least one of them is. Let's try to use the conditional probability formula in a way to arrive at the answer to this question. Both cards being hearts is a probability that we did in the last problem. In fact, we did it two different ways. So if you go back to the last problem that we just did, and remember the answer that we obtained, we already know for starters here that the probability that both cards are hearts is 1 over 17. Now in this case, what is B intersect A? What do you get if you take all the cases where both cards are hearts and intersect that with all the cases where at least one of them is a heart? Well, obviously, any case where both cards are hearts is a case where at least one of them is. So in fact, every outcome that's in B is an outcome in A. This event is a subset of this one. So the probability of the two, the probability of the intersection, is just the probability of B. B intersect A is B in this case. So the probability of B intersect A is just the probability of B, which is 1 over 17. But now what about the probability of A? The probability at least one of them is a heart. Let's take the backdoor approach to that. Remember, we can always calculate the probability of an event as 1 minus the probability of its complement. Why is that an attractive approach to this question? A is the cases where at least one of the cards is a heart. What would the complement of A be? It would be all the ways in which you can deal two cards in which neither one of them is a heart, which means we're looking at cases where the two cards dealt come from the other three suits, clubs, diamonds, and spades. So to find the probability of A, we can do 1 minus the probability of the complement, and we can calculate the probability of the complement just as a counting problem. All the possible, count the number of possibilities when we deal two cards from a deck, and for the numerator, take the number of possibilities where the two cards come from the diamonds, clubs, and spades, the 39 cards which are not hearts. So here we're counting the ways to get a pair of cards, neither of which is a heart, and the reason we're doing it is because that's the complement of the event A. Do that counting. These two uses of the combinations formula reduce to 19 over 34 when you do that arithmetic. 1 minus 19 over 34 is 15 over 34 as the probability we're interested in, P of A. So let's put it all together now. The question was, what's the probability both are hearts if we know that at least one is? And what we have done so far is do the work necessary to know what number this probability in the numerator is and what number the probability in the denominator is. The numerator we determined to be 1/17, the denominator 15 over 34. Do the arithmetic and we get 2 over 15 as the probability that both are hearts if we know that at least one of them is. Now we move to 5 people consisting of 2 men whose names we know and 3 women, and we have names for the women as well, are on a committee. 2 of the 5 are to be chosen to serve as officers. If the officers are chosen randomly, what's the probability both officers will be women? We know how to do this problem just by counting. We can count the possible outcomes for choosing 2 of the 5, and we can count the number of those cases where the 2 chosen would be from the 3 women, and we find that there are 10 possible outcomes, 3 of which would give us 2 women as our officers, so that's a probability of 3/10. So again, if we do this problem strictly by counting, we're not using the concept of conditional probability, and one indeed does not need the concept of conditional probability in order to do this problem. But let's show that there's an easy alternate solution. Think about picking the members of the committee one at a time. When you're picking the first committee member, you're choosing from 5 people, 3 of whom are women, so that's 3 chances out of 5 that the first person chosen is a woman. Now, if you know the first person is a woman, what are the chances the second person is a woman? When you come to the second person, you would be left with 4 people, of whom 2 of them are women, if you know the first person is a woman. So that would give you 2 chances in 4 of the second one chosen being a woman. 3/5 times 2/4 is 3/10. So this is another way of doing the problem, not doing counting, but doing conditional probability instead, which again leads to the correct answer. And the rationale is we're computing the probability that both are women as the probability the first is a woman times the conditional probability the second is a woman if we know the first is a woman. So we're doing the same kind of trick that we've done before, using the conditional probability formula as a way of determining the probability of the intersection, that is, the probability both are women. Now notice in this second solution, we're thinking of the selections being made one at a time. I'm talking about the probability the first is a woman and the probability the second is a woman. It doesn't really matter whether they're actually chosen one at a time or not. We can think of them as person number 1 and person number 2, no matter whether they're actually chosen one at a time or simultaneously. So think of this as just a trick way to think about the problem. And it really doesn't matter what process is actually used for selecting them, whether they're selected concurrently or one at a time. Let's now switch over to the question, what's the probability at least one of the officers will be a woman? This is another one of those cases where it's an easy way to do the problem to turn around and look at the complement. What we want to know is the probability at least one is a woman. That's 1 minus the probability of the complement event, and the complement of saying at least one is a woman is to say that they're both men. The probability they're both men we can get by simply counting all the cases and dividing that into the number of cases where the 2 people chosen are from among the 2 men, which is just one of the 10 cases. So that's 1 over 10, 1 minus 1/10 is 9/10 as the probability that at least one is a woman. If you have any doubts at all about what it is we're counting or what we're really doing, sit down and list the 10 possibilities, just as we did when we talked about the 10 possibilities for 5 people applying for a role in the play. Now let's change the question again and say, what's the probability both officers will be women given the information that at least one is a woman? I've written the conditional probability definition in here again. So let's think of B as being the event both are women, and A being the event at least one is a woman. So the probability of B happening if we know that A happens is saying, what's the probability both are women if we know that at least one is a woman? And the definition of conditional probability says that this is equal to the probability both things happen, which is that both are women and at least one is a woman, divided by probability of A, which is the probability at least one is a woman. Saying that both of them are women and at least one is a woman is the same thing as saying that both are women. So the numerator we can rewrite this way. Both of them being women has probability 3/10 as we already calculated. At least one being a woman has probability 9/10 as we previously calculated. So this fraction reduces to 1/3 the chances that both are women if we know that at least one is. And if you were to take the time to go back and list all 10 of the possible outcomes, what you would see is that the reason this reduces to 1/3 is because the given information reduces those 10 outcomes down to 9, of which 3 of them are cases where both officers are women. And a final variation on the question, what's the probability both officers are women if you know that Beth is an officer? Another conditional probability question, we're asking what's the probability both are women based on the information that Beth is an officer. The definition of conditional probability says we can get that by looking at the probability both things happen, which says both are women and Beth is one of them, divided by the probability of the given information that Beth is an officer. So we have to fill in these two probabilities in order to determine the conditional probability. For the numerator, we need to fill in the probability that both are women and Beth is one of the officers. Well, let's just go up and look at the list and think what cases those are. How many ways can you have 2 officers where one of them is Beth and both are women? To have both of them be women and one of them be Beth, you've got to have either Ann and Beth or Carol and Beth, right? Those are the only 2 cases out of the 10 where you have 2 women with one of them being Beth. So this probability upstairs is going to be 2/10. Downstairs, we need to fill in the probability that Beth is an officer. So how many ways can you have 2 officers where one of them is Beth? You either have to have Beth and Jim, or Beth and Bob, or Beth and Ann, or Beth and Carol. So that's 4 ways out of the 10 that you can have 2 officers where one of them is Beth. So the numerator here is 2/10, the denominator is 4/10, and that reduces to 1/2. 1/2 is the probability both officers are women if you know that Beth is an officer. And if you were to list the 10 possible outcomes, what you would see is that the given information that Beth is an officer reduces you to 4 cases, and 2 of those are cases where both officers are women. So that's intuitively why the answer should be equal to 1/2 in this case. A baby has 5 blocks in a bucket. A red one, a yellow one, a green one, a blue one, and a black one. And 4 times the baby is going to reach into the block, to the bucket, pull out one of the blocks, and put it back. Our question is, what's the probability that the baby pulls out specifically the red block first, the yellow block second, the blue block third, and the green block fourth? The key thing here is that each time the baby reaches into the bucket is full of blocks. So any time the baby does that, there are 5 possibilities for which block can be drawn. So that's 5 possibilities for which color block the baby draws first, and then because the baby puts it back, that leaves 5 choices for the second, the third, and the fourth attempt. So the number of different possibilities is 5 choices for the color of the first block, 5 choices for the color of the second, 5 for the color of the third, and for the fourth. So that's 5 times 5 times 5 times 5 possibilities for the sequence of colors that we'll get. 5 to the 4th power is 625. So there's 625 possibilities for the sequence of 4 colors that will be obtained when the baby does this. Now, of those 625 possibilities, the particular sequence red, yellow, blue, green is only one of the 625 things we just counted. So the probability of this specific color sequence being the one that occurs is one chance out of the 625 possible chances for the sequence of 4 colors that's obtained when the baby does this. In the next variation, we'll ask what's the probability the 4 blocks selected are all the same color. Well, there are 5 color sequences that would produce 4 blocks of the same color. The baby might select the 4 red blocks on the 4 draws. Well, there's only one red block. He might select it all 4 times because the block is returned to the bucket every time, remember. So the baby might get the red block the first time, the second time, the third time, and the 4th time. Or the baby might get the blue block every time, or the black block every time, or the yellow block every time, or the green block every time. Those are the 5 color sequences that would produce a sequence where the 4 blocks drawn are all the same color. That's 5 of the 625 color sequences we just counted. 5 over 625 is 1 over 25, a probability of 1 over 125. A probability of 1 over 125 that the 4 blocks selected are all the same color. Next variation on the problem says what's the probability the blocks are red, yellow, blue, green in that particular order if we know that the blocks the baby chooses are different colors from each other. So if we know the blocks are all different colors in the 4 experiments, what's the chances it's that particular color sequence, red, yellow, blue, green? So this is a conditional probability question. What's the probability we have that particular sequence if we know that the 4 draws produce 4 different colors? So let's just plunge into this using the definition of conditional probability. The probability of this happening based on the knowledge that this happens is the probability that both things happen divided by the probability of the given information, which is that we have 4 different colors. Now, in the numerator, saying that we have this particular color sequence and all different colors, of course, reduces to just saying that we have this particular color sequence, because obviously if you have red, yellow, blue, green, then you have 4 different colors. So the numerator reduces simply to asking what's the probability of this particular sequence. And we know that that's 1 over 625 because this color sequence is only one of the 625 possible outcomes. For the denominator, we have to think about the probability of getting 4 different colors in the baby's 4 selections. To get 4 different colors, we could have any one of the 5 possible colors for the first block drawn, and then any one of the 4 other colors for the second block drawn, 3 remaining colors for the third block, and 2 for the 4th. So that's 5 times 4 times 3 times 2 possibilities for a color sequence where all the colors drawn are different out of the 625 possible color sequences. So this is what number agrees with the probability in the denominator. And if we do the arithmetic here, cancel the 625s, that's 1 divided by 5 times 4 times 3 times 2, which is 1 over 120 as the conditional probability that we're looking for. And finally, to a coin tossing example. If a coin is tossed 3 times, what's the probability all 3 tosses come up heads if we know that at least 2 of the tosses come up heads? We have a picture here showing the 8 possible outcomes if you toss a coin 3 times. Heads, 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 heads on the first 2 tosses, tails on the third, a head followed by tails followed by head, and so forth. Why is it 8 possible outcomes? Well, each time you toss the coin, it's either going to come up heads or tails. That's 2 possibilities. 2 possibilities for toss number 1, 2 possibilities for toss number 2, 2 possibilities for toss number 3. 2 times 2 times 2, the multiplication principle, gives us 8 possible outcomes for this experiment, and the 8 outcomes are shown right here. Now, we're looking for this conditional probability, the probability that all three come up heads, knowing that at least two do. So the conditional probability we're trying to compute is shown right here, the probability of 3 heads based on the knowledge that we have at least 2 heads. The intersection of these two events, if you say all the cases where we have 3 heads and at least 2 heads, that's the same as saying all the cases where we have 3 heads, and that's just this one case right here, one of the 8 outcomes, probability 1/8. In the denominator, the cases where we have at least 2 heads, the probability of that, well, those cases are the cases that have green arrows pointing at them. 4 of the 8 cases are cases where we have at least 2 heads in the 3 tosses. So the probability of that happening, the probability of at least 2 heads, the probability shown in the denominator here, is 4/8, 4 of the 8 outcomes. The fraction reduces to 1/4. So based on the knowledge that we have at least 2 heads, the probability of all 3 being heads is 1/4. You can see that in the picture. Anytime you have all the outcomes listed, you can see things without needing a formula like this. So what we're doing is using the formula to verify what we can see in this example. And of course, in cases where the sample space is too big to list all the outcomes, that's when you would have to use the formula in the approach that we're using here. But to see them in this particular case, we started out with the 8 outcomes. Knowing that we have at least 2 heads narrows it down to the 4 which are pointed at, and one of those 4 has 3 heads, so that's why we come out with 1/4 as the answer.